Alright guys, welcome back to my channel. This is like Fluids 101. Today we're going to be taking a look at very important topic, which is Reynolds transport theorem. Alright, so first off, we're going to start with we're going to be deriving this, and we're going to start with the basics. We're going to start with conservation of mass. Alright, so if you are unfamiliar with the law of conservation of mass, no worries. It's just that mass, cannot be created or destroyed. That mass is like a fixed amount. So we're gonna have this right here, right? We're gonna have dm, which represents our change in mass over change in time of our system, is equal to 0. Boom. All right. So we're gonna start there, and now what we're gonna do is we are gonna express this as like a rate. Well, it's best as a rate here, sorry. So when we have this dm, right? So if we separate these, if we separate dt and dm, we can say that the mass of a system is equal to, and this is just going to be our mass system dm. Alright, now for fluids, we want to work with a volume, right? It's easier to work with a volume and density terms. And I'm going to get into that a little bit more to help you guys out. So how can we rewrite mass in terms of density? So we know that relationship between mass density and volume is we're going to be denoting density with rho is equal to mass over volume, right? So what we can do here is we can take so mass can be rewritten as rho times v. So we're gonna essentially have this dv. This is a rho, okay, rho. Don't confuse this with pressure. This is rho, and this is gonna be the volume of our system. Okay, so now let's actually go into Newton's second law really quickly. So Newton's second law, is that the force is derivative of momentum. Okay, and that's just because we know that this is mass times velocity. That's what momentum is equal to, right? And mass times velocity, you take the derivative of that, holding mass constant. Sorry, you have this, So now let's take a look at what we can do from this. So we got mass, we got velocity. Mass can be rewritten in terms of density, right? So this can be rewritten as V, representing the volume, times density, right? That's mass, and we're going to make that a little dv, and we're going to have our velocity vector, and then, wait, I made that volume. This means velocity. This arrow on the top is just going to denote that this is just going to denote that this is a vector when we have that little arrow above. So volume of our system. So there we go. This should be our system. So we got our little equation right here to represent linear momentum in terms of volume. Okay. Now we can also replace depending on angular momentum. Angular momentum is, if you're familiar with it, it's like r cross v, right? And you can have, it's r cross f, r cross f, and f is, you know, we have our this right here, this thing right here, D. So if we rewrite this, we can actually cross R with the V right here. And so you can see that a lot of these properties that we have, these principles and these laws, they can be rewritten using this density and this volume, this volume for systems. So now that you know this, we can also even take things like energy. We can put energy in there, and there's a couple of things we can put in there. The main thing to just note is that we want our properties, we're gonna give any like an arbitrary property, this letter, it's like little n looking thing. So if we have this property for a system, and we can have it, so n can represent like, you know, mass, momentum, energy, entropy, and you can have that equal to this versus the control volume, or the volume of the system, density dV. Okay, so now let's go ahead and see what we can do with this. So before we derive this volume, of a system, we need to understand like the derivation of just like some random like piece of like fluid flowing. Okay, so we have what's called this volume, right? This volume system. You might have seen that earlier. I referred to it as a control volume a couple times. I said like control volume. So what is that control volume? So if we have this fluid, right? Okay, and we have our, you know, x, y, z, and we pick some area in like a space, right, to encapsulate this fluid, and we want to observe the system, right? Could be, you know, momentum. It could be energy, right? So this is just a random control volume, okay? That I made, just random control volume, okay? And we have it at time t0. So this is a control volume. So another way to imagine control volume is if you have like, I don't know, like let's say you have, oh, this is such a bad drawing. You have this little perfume bottle, okay, and this is where your perfume is stored. This is your control volume. Okay, so we have this control volume at time t equals 0. Now let's see what happens. So this control volume also encapsulates my system as well. Control volume, so this is time t0, control volume, and my system as well. So actually, like this area that's shaded, I'm gonna shade this area in. This red shaded area is my system. So my control volume is like this drawn out thing that's around here, and this red thing is equal to my system. So let's take a look at a time in the future. So this is going to be time plus delta t. Okay, so now this is going to be a little wonky drawing, but try to follow along. We're going to have our control volume. Our control volume is the same, okay? I'm trying to make it the same shape, okay? And our system moved, okay? System moved. Okay, and we have, now we're gonna have these three regions, okay? Region 1 is gonna be this region right here, okay? This surface that's right here. Region 2, that's like the overlapping surface between the system and the control volume. And region 3, we can see like the systems ahead. So we have these, what's called these control surfaces. So when you think about spraying a perfume out, like the nozzle and like the exit of your perfume, you can have like your control surface there. Or actually, my control volume should be more up here so that I can encapsulate my control surface there. But anyways, so now we have our system. We have these three regions, and now we're gonna see what can we actually do with these regions. Like, how can we get to the derivation, okay? So now we're going to take a look at the change in our system with respect to time. So if you remember up here, we had the end system, and here we had so we went from that to that, and I use that to lead off into this. And now we think of taking this back to that. It's a little confusing, but you'll see what I mean. So now we have this system, right? And in order to evaluate this, what I'm going to use is the definition of a derivative. So we're going to see as our time goes to 0 limit, we're going to have our system. Remember, our system times 0 plus delta t minus, this is just the definition of a derivative, if you guys remember from calculus 1, over delta t. So now let's take a look at what we can work with here, how we can translate these terms. So our system at time t, we have this surface there, which is system 3. That's the region 3 of the surface. So n3, okay, and that's gonna be plus, and now we're gonna have our now this right here is gonna be this region that we had. So you think of it as like the control volume, right? Mine plus n CV minus n 1. So now we got this addition, right? This region here that we're getting, and this region that we're moving out from, and we have our control volume, okay? And now this is at t0 plus delta t minus, now what is the system initially? Now if you remember, I said initially the system and control volume are the same thing, so we can rewrite this as ncv, the initial time, all of this over delta t, okay? And remember, the limit needs to follow. So now, after we have this, what we can do is that the limit of the sum is the same as the sum of the limits. What that means essentially is that I can kind of rewrite this as by breaking apart everything. So I can have NCV initial plus minus NCV. Now you're gonna see there's a reason why we did this, because this is like a really good definition of this is like perfect for the derivative. So this is gonna be as t approaches 0, and we're just gonna break it apart. So now we'll have n3 okay, and we're gonna have minus limit as delta t approaches 0. Approaches 0 over delta t. Okay, so now we have these terms, right? Term 1, the galaxy pen, term 2, and term 3. Let's take a look at what we can do with these terms. So this term right here, what we can actually do with it is we can turn this into a partial derivative, right? Because this is like perfectly set up in the form of a derivative, and yeah. So okay, so now we have this, and what we can do is we can if you remember earlier, let me see if I can find it, this n system is equal to that, right? So we can take this n and transform this into, we have control volume for the system, and we had this density, we had this property, and we had UV. So this is rho, remember density. So now we have this first term, okay? Now let's take a look at what we can do with these second and third term. So if we want to evaluate this second and third term, we need to look at like a region, okay? So we take a look at like this region up here, which is region 1, region 2. If we take a small little area of that, we have the fluid flowing in and out of that, right? Kind of like it's kind of like an area where the fluid flows out, right? And so now we have this area, right? And we have this area for 3 and we have this area for 1, right? So if we just wrote it like this, right? I'm gonna bring this down here, or yeah, or actually we're gonna do this one, the and region 3. Okay, this system at the region 3. So this this is equal to, and it's just gonna be, right, we went through this a couple times earlier, but actually we only have the area, right? We have this region, this area. This region is an area. That region 1, that region 3, those control, those areas, the surface areas, we need to figure out a way to model them as volume. We need to obtain volume, right? So we have our control surface, and we have like the system boundary. So that's the control surface right there, which is going to be that region where our system is like going away from, or that region of our control volume, these new surfaces, right? So like an example would be the outlet of that spray. So how can we write this? So if we have the velocity of our fluid, right? And velocity is like distance over time, or like we can model like it as length over time, right? Equal to change in, yeah, so change or change in time. So we can actually rewrite this distance, or actually I'm gonna use this, it at okay, it's gonna be L, okay, L over, okay, so this, if this was just an area, right, and we have this area, we want to transform this by figuring out like this height, right? That's how we make it a volume. That's how we extrude it, right? So we're actually gonna multiply V by T, okay? But and that's gonna give us this length, right? But before we do that, remember when I said we were looking at the fluid that flows out of that region, right? So what also matters is that angle that our fluid flows out of this, right? This region, this control surface, this angle matters. The angle between the velocity and what's called the normal vector, or the area vector. The area vector is just equal to the area times the normal vector, and the normal vector is a unit vector. That means that the magnitude is 1. If you guys remember from calculus 3. So the normal vector always points out in the direction of our surface. If we have this area, normal vector is going to point out like that, okay? So in order to figure out how much fluid crosses that region, we need a dot product, or yeah, we need a dot product to basically model, because that shows the cosine dependence, right? So now let's see. So we have this, we have density, we have area, and now we need to make a dot product. So we have velocity dA delta t. Remember that v times delta t is equal to this. So this is what's making it a volume. This is what's making it a volume. Okay, and we're gonna have our density and this, and so that is same thing as this. So now we have this differential element, we can integrate it across the whole region, right? So and so we have this differential, so now we need to integrate it to put that here, right? So we're gonna have this control surface, and we're gonna have all of this stuff, which is gonna be, so control surface 3 is gonna be and we should be left with now this is the final expression for this is the final expression to model the control surface. So if you actually see, these two are essentially the same thing, but in one of them the fluid is coming in and one of them the fluid's coming out, which means that the only thing that varies, that means that they're pretty much the same thing. The only thing that will be different is this A, because you remember I said that if we take a look at this pipe, we have the fluid flowing like that, right? Our area vector in this direction is going to be going like that, and that's negative. So you have a negative n here. This one's positive, so that's going to make, we're going to have like a negative, and we can make, depending on the control surfaces, we'll have different other integrals, right? So now that we have these two, we can pretty much combine them, and control surface 3, since the equation is the same as control surface 1, we basically combine them under the general term control surface. So if we combine the control surface and the control volume, that shows the control volume is the storage and the control system is like the transport. So putting everything together, you get this. And this, remember this property, it's important to know what this means. dt, and this is going to be the control volume. You're going to have rho control surface, and this right here, ladies and gentlemen, this is the Reynolds transport theorem. And yeah, so the purpose of this whole video was just to show you the derivation of this, and next video hopefully we can go over some practice problems. Main thing I want you guys to know is, like, to help you guys understand this, is imagine you have this tank. Okay, oh, hold on. Imagine you guys have this like tank, okay, holding this fluid and it's pouring out through here. You can model this as your control volume. Your control volume, you can pick what your control volume is. Control volume, and this right here is your control surface. So yeah, thank you guys for watching, and I'll see you guys in the next video.